Alright, so today we're going to discuss the final class of reactions, double replacement reactions. So double replacement reactions have a form that looks something similar to this. So we'll just use generic symbols here. AB plus CD yields AD plus CB. Okay. So you can see here that the A and the C switch places. So typically, if A and B and C and D are ionic compounds, the metals will switch places. So I know I've talked about phase symbols quite a bit, and I've used them in a lot of situations, but not all situations. Typically, previous to this point, I only used phase symbols really in two situations: when the phase was explicitly discussed in the problem. So if it said solid iron, for example, or if we produce something that we knew was a gas, like hydrogen gas or oxygen gas. But for double replacement reactions, I always have to use phase symbols, okay? And it'll be up to you to determine what the phase of each of the reactants and products actually are. So we're going to spend some time discussing how to do that here. So first off, let me mention that for double replacement reactions, you'll always start off with two aqueous solutions. Okay, so AQ, AQ. So that could be written out in words a lot of different ways. So you could actually see an aqueous solution of AB written out. You could see a solution of AB written out. Or you could say compound AB is mixed with water and dissolves. Okay, so all those tell us it's an aqueous solution, so the compound dissolved in water. So the products, one of the products will be an aqueous solution, and the other product will either be a solid or a liquid. Okay, so it's very important to note that we'll produce most of the time a solid, and if not a solid water, which we will consider to be a liquid here. So we know this is the general pattern, and we know that one of the products is typically going to be solid, but we have to look at some rules to determine which of the products is going to be solid. Okay? So if you look in your notes and find a couple of pages down, you have a solubility table listed on a page all by itself. Okay, so this is a chart that you'll always have access to for reference, and it's a chart to help you determine what compounds are soluble in water. Okay, so if a compound is soluble, so let's just say compound AB, if it's soluble in water and it's mixed with water, it dissolves. Okay, so it gets the symbol AQ. If compound AD, for example, and I'm just going to make one up, I guess it's better to say CB here, stick with the original example, it is insoluble. Okay, so if it is insoluble in water, that means it cannot be dissolved, so it gets an S. Okay, so don't get that mixed up. The S here corresponds to solid. Okay, so that means it's insoluble or not soluble, cannot be dissolved. So some people get confused and they associate soluble with this S here, so don't get that confused. So let's look at how to read this table. Okay, so let's start on the first line. This says nitrates, chlorates, and acetates are all soluble in water. Okay, so if you have potassium nitrate, if you have ammonium chlorate, if you have copper 2 acetate, any ionic compound that contains a nitrate, a chlorate, or an acetate dissolves in water. Okay, so that's a fairly simple rule. The next line, if you have a group 1 metal or ammonium in a compound, they are soluble in water. Okay, so that's fairly simple as well. So if you have sodium, lithium, potassium, any of those metals down the column, or ammonium as your cation, you want to be soluble. The next rule, sulfates are soluble in water, except barium, calcium, strontium, silver, or lead 2 sulfate. So let's look at that. So it says sulfates are soluble, so Na2 SO4. Okay. So if the rule says sulfates are soluble, is sodium an exception? No, it's not. So when mixed with water, sodium sulfate would dissolve. But then let's look at silver sulfate, Ag2SO4. So it says sulfates are soluble, but it says except for, and there's several exceptions, and silver is an exception. Okay, so silver sulfate is not soluble in water. So when silver sulfate was mixed with water, you would not see it dissolve. It would remain a solid. So if we look at the halogens, the same kind of thing goes on. Halogens are soluble except for, and it gives you some exceptions. So NaCl, for example, could dissolve in water. So if you mix it with water and try to make it a solution, you would see an aqueous solution. But HgCl2, mercury 2 chloride, you would see a solid because mercury 2 is an exception. Notice for the transition metals it gives the specific charge that is an exception. So something like HgCl, you can see that chlorine's -1, so that means this mercury has to be +1 for the charges to cancel. So this compound would be aqueous. Okay, so mercury on its own is not an exception to the rule. Mercury 2 is an exception to the rule. So the next two rows are a little bit different. Carbonates, phosphates, chromates, sulfites, and hydroxides are insoluble except for the alkali metals or ammonium. Okay, so their standard rule is they're insoluble. So let's look at iron 2 carbonate. Okay, so iron 2 carbonate, look at the rule, carbonates are insoluble except for the alkali metals and ammonium. So iron's not an exception, so insoluble, we get a solid. So if you look at one of the exceptions, we could say Na3PO4. So we see the rule, phosphates are insoluble. Okay, so our instinct is to put insoluble, so that means it's a solid. But we look at the exceptions except for alkali metals. So sodium is an alkali metal, so this compound is soluble here, so it gets AQ. Same thing for sulfides. So sulfides are typically insoluble. So something like CuS, copper 2 sulfide, would be insoluble. But there are exceptions. So group 1A, group 2A, and ammonium sulfide compounds are soluble. So if I had calcium sulfide, CaS, that would be soluble. Okay, so soluble gets AQ. Okay, so the rules are fairly easy to read. You just have to pay careful attention and make sure you carefully read the chart each time. And again, this will be something you always have access to. Just pay close attention to the last two rules. Okay, notice the last two rules. The base rule is insolubility. Okay, and the exceptions mean that it is soluble. So you might see there are some overlap with some of the rules. So anytime there is overlap, the same rule will apply. So if you had NaCl, for example, sodium chloride, so right here, there are two ways to check this for solubility. You could go to the second row of the chart, because sodium is a group 1 metal, and find that it's soluble. Or you could go to the halogens row of the chart, because chlorine is a halogen, and see that it's soluble as well. So anytime there is rule overlap, use whichever one you come across first, and you will get the same outcome each time. Okay, so the reason why these rules are so important is we use these rules to determine if a double replacement reaction actually happens. So just as with a single replacement reaction, a double replacement reaction might not happen. Okay, so no reaction is a perfectly valid solution or the only correct solution in some situations. So we're always going to mix two aqueous solutions together. Okay, so the problem will tell you solutions of two things are mixed together. So we don't need to check the solubility for the reactants. Then we'll need to write out the products, which we'll talk about doing in a moment, and we'll check the solubility for the products. If both products are soluble, that means they dissolve in water and they're an aqueous solution, then we have no reaction. Okay, so if you produce two aqueous products in a double replacement reaction, you have no reaction there. Okay, so double replacement is a little bit different. You still have to write the products out, the predicted products, to determine if the reaction happens. Okay, so what you do there is go ahead and write an X over the arrow and probably write no reaction over the arrow as well. So I know that was a lot of words. It might be confusing just talking about it, so let's look at a couple of examples of these. So listed in your notes, there are three classes of double replacement reactions. The first class is by far the overwhelmingly most important and most common class, so we're going to spend the majority of the time looking at that, and then we'll look at one of the second and third classes when we get done. So let's focus on the soluble salt plus the soluble salt. So again, remember, a salt in chemistry just refers to an ionic compound here. Okay? So we start off with example 1, and I'm going to go ahead and write this out in words so you could see what it might say. So we could say solutions of mercury 2 nitrate and sodium chloride are combined. Okay. So we can be instructed to determine if the reaction occurs, predict the reaction, and then I might ask you, what is the solid product? You'll often be asked to circle the solid product. So the first step is, when you're given a chemical reaction in words, is to write out the reactants in symbols. If you can't do this, then you can't solve the problem correctly. So I have mercury 2 nitrate, so I have HgNO3 2 plus sodium chloride and HCl. So the problem told me solutions of these compounds. Okay, so the phase symbol for solutions would be AQ here. So I'm kind of running out of room. I wrote a little bit too big here. So I'm going to draw the arrow kind of like this. That's not a great way to do it, but just so I have more room to write the products here. Okay. So I know the two metals are going to switch. Okay. So mercury and sodium are going to switch. Whichever you want to write first is perfectly fine. Let's just start with mercury. Okay, so mercury, instead of being paired with nitrate, will be paired with chlorine. Then I have to go back and check my charges. So here, mercury was +2, chlorine was -1, so I cross my charges, HgCl2, plus, remember I always write the cation first, I always write the metal first, so Na, then NO3. Sodium's +1, nitrate's -1, so I'm in good shape there. Okay? So before I go and balance this, I need to get my phase symbols correct. Okay, so now I go to my solubility table. Okay, and again, if you wanted to flip these products, that's perfectly okay. You could write sodium nitrate first. So let's look at sodium nitrate first. So there's two ways to check this. I can look at row 1 and see that nitrates are always soluble, or I can look at row 2 and see that group 1 metals are always soluble. So either way, I get the same answer. Okay, so I have a Q. Okay, so sodium nitrate is soluble, so it dissolves in solution. So mercury 2 chloride. So let's go to the halogens row. So I see that halogens are soluble except for silver, mercury 2, lead 2, and copper 1. So do I have an exception here? Yes. Mercury 2 is an exception to the halogen solubility rule. So because it's an exception, I have a solid product. Okay? So because I have a solid product, this reaction does happen. Okay, so I'm in good shape. So now I can go through and balance my reaction. I can put a 2 there, put a 2 there. Now we're all balanced. Let's think about what this might look like. So if you mix these two solutions together, so you mix two dissolved compounds, they might be clear, they might have some kind of color tint. You combine them, and then you get a solid that forms. Okay, so you get a precipitate that forms. So there will be a solid in the bottom of the flask there. Okay, so we'll do this several of these reactions in lab. They're fairly interesting reactions to look at. So let's look at another one. And I'm going to go ahead and write out the symbols here. Again, this will be presented in a word problem most likely, but we'll go ahead and start off with the symbols here. So I might have CuCl3 plus lithium bromide. Those are aqueous solutions. Okay. So the first step is you have to figure out what kind of reaction is this. Is it combustion? It can't be combustion because there's no oxygen. Is it decomposition? It can't be decomposition because there is more than one reactant. It doesn't look like a single replacement reaction, and it doesn't fall into one of the synthesis patterns we learned. Does it look like a double replacement reaction? Yes. It's aqueous solutions of two different ionic compounds. Okay, so we know what to do with it. So we know the two metals are going to trade places essentially. So let's start with the copper. So CuBr. So I know bromine's -1, but what's the charge of copper? It can vary. So I have to come check over here. I know that chlorate is -1 because I learned my polyatomic ions, so I know copper has to be +1 to cancel out there, okay? So copper here was +1, So then I have plus LiClO3, lithium chlorate. Lithium's +1, chlorate's -1, so I'm in good shape there. Okay? So now we have to check the solubilities. Lithium chlorate. So I look at the first line, I see that chlorates are always soluble, no exceptions. Okay? So I'd put in AQ. Okay? Sorry, running the room there. So that is an aqueous solution. And then I look at copper 1 bromide. So I'll find the halogens. Okay? I see that for the halogens, they are typically soluble. Okay? But I continue reading and see that there are exceptions. So copper 1 is an exception to the halogens being soluble. So because it's an exception, a solid forms. Okay? So this reaction actually happens. Then if I ask you to name the solid product or circle the solid product, I can name the solid product copper 1 bromide here. So let's look at one more of these. Let's look at sodium sulfide. So Na2S, I'll go ahead and write AQ, plus NH4Cl. Okay. So here, I only have one metal, but we know ammonium behaves as a metal, is a positive polyatomic. So I see that it's a double replacement reaction. So I'll go ahead and put NaCl plus NH4S. I cross my charges, and I had NH4 subscript 2S because I have a +1 and a -2 charge. Okay, so I go ahead and check my solubilities. I have sodium chloride. I see that that sodium group 1 metals are always soluble, so I get an AQ. Then I check sulfides. Sulfides are insoluble except for group 1A, group 2A are ammonium. So this rule is written backwards, so sulfides are insoluble except ammonium. Okay, so because it's an exception to this rule, it would also get the AQ phase symbol. Okay, so I'm producing both aqueous products. So what does that mean? That means when you combine these two solutions, you don't form a solid. The solutions just mix together and nothing happens. So I get no reaction. X over the arrow, then a capital N, capital R. Okay? So when you see a double replacement reaction that does not produce a solid or a liquid product, no reaction happens. You still have to write the predicted products out though, because that's the only way to determine if the reaction happens or not. Okay, so that is the most typical form of a double replacement reaction. You have two solutions of ionic compounds and they combine to make either a solid product and an aqueous product, or two aqueous products. Okay, so that's the most common form. Fairly simple, but let's go and look at the two other types of examples of double replacement reactions that we'll run into. So label number 2 in your notes, you have carbonates plus an acid. Okay, so numbers 2 and 3 in your notes are really acid-base reactions that we'll discuss more in May, but they still fall into the category of double replacement reactions. So I'll introduce you to them here, but we will focus the majority of our efforts on the first class of double replacement reactions. Okay, so the second section of your notes says carbonates plus an acid produce salt plus CO2 plus H2O. So again, that's not sodium chloride salt necessarily. It could be. It is just the ionic compound that results from the reaction. So let's look at one. Let's look at K2CO3 plus, we'll just say HF. And one other thing, I just realized this. I didn't go back down here and balance this reaction, so you know that you would actually need to, if you were doing this, we would put a 2 in front of the sodium, a 2 there, and we're in good shape now. So don't forget to go back and balance. Okay, so here I have a carbonate plus an acid, so I could say, these are aqueous, for example. Okay. So you just have to recognize when you have a carbonate plus an acid is a special class of double replacement reactions. So let's go ahead and write out the products that are always the same first. So I always have CO2, CO2 is going to be a gas, plus H2O liquid. So remember, if a double replacement reaction forms a liquid, or if it forms water, the reaction is going to happen. Okay, so I know the reaction is going to happen. Now I need to figure out what the salt is. Okay, so let's look at the reactants. So I've already accounted for hydrogen over here. I've already accounted for carbon and oxygen. We use what's left over. So I have potassium and fluorine. So my salt is Kf. I could check, most likely these will always be soluble. In this case it is. So I get that right there. Okay. So this is technically a double replacement reaction, but you'll recognize it doesn't quite follow the typical form. So just for now, just be aware this type of reaction exists. We will see this more in the spring when we look at acid-base reactions, so don't worry about these too much for now. Just be aware that they exist. In the third class, we have an acid plus a base. So we can think of the most common acid, NaCl, Aq, plus a base, NaOH, Aq. Okay. So the products are always going to be the same here. We'll have H2O liquid plus the salt that's left over. So here, NaCl, Aq. Okay. So an acid plus a base yields a water plus a salt. This is called a neutralization reaction. So this is the classic acid-base type reaction that we'll look at in the spring. So for now, just be aware that it does exist, so you can probably see how the hydrogen and sodium switch places, and instead of writing HOH, we just write H2O. Okay. So focus on this one in the first type. Don't worry so much about this one. This is really no different than the first class of double replacement reactions. The only difference is instead of writing HOH, you write H2O liquid. Okay. So those are the basic rules for double replacement reactions that we'll look at this year. A couple of points to remember. You need phase symbols. Okay? Everything has to have a phase symbol. Don't just make them up. Okay? Use the solubility table. You have access to it. The few times that you won't use the solubility table are when you form CO2 and when you form H2O. We know the phases of those automatically. Okay? So if there is no solid or liquid product, we get no reaction. Okay? But you still always have to predict products. And I know a lot of times with single replacement reactions, we didn't have to predict the product. We could tell if it happened or not without writing the products. But in order to predict the products of double replacement reactions, you have to go ahead and predict the reaction all the way through. Okay. So don't forget to check charges. What do I mean by that? So if you have something like CaCl, don't get in a hurry and forget to check your charges. Plus 2 minus 1, cross it and get CaCl2. And then lastly, this is a very easy mistake to do. I made it a few minutes ago. Don't forget to go back and balance. That's by far the easiest part of this whole thing, so don't lose easy points there. And then don't be intimidated if it asks you to write the solid product in words. Okay. So for a lot of these examples, you'll see something like this. It'll ask for the solid product in words. It's just copper 1 bromide. Okay, so don't be intimidated by that.